Helicopter Flying Handbook 11.3 Helicopter Emergencies and Hazards. In forward flight, the relative airflow through the main rotor disc differs between the advancing and retreating sides. The advancing side experiences higher airflow due to the helicopter's forward speed, while the retreating side has lower airflow. This dissymmetry of lift intensifies with increased forward speed. To maintain equal lift across the rotor disc, the advancing blade flaps up, decreasing its angle of attack, AOA, and reducing lift. Conversely, the retreating blade flaps down, increasing AOA and lift. As forward speed continues to rise, the retreating blade, with its low speed and high AOA, eventually stalls, resulting in a loss of lift. Retreating blade stall is a critical factor limiting a helicopter's never-exceed speed, VNE. Its development is indicated by low-frequency vibrations, nose pitching up, and a roll toward the retreating blade. Factors such as high weight, low rotor RPM, high density altitude, turbulence, and sharp turns contribute to retreating blade stall at high forward airspeeds. As altitude increases, higher blade angles are required to maintain lift at a given airspeed, causing retreating blade stall at lower forward airspeeds. Recovering from a retreating blade stall caused by high airspeed involves careful consideration of factors. Moving the cyclic aft exacerbates the stall, and pushing it forward deepens the stall. While reducing collective is a typical first step in recovery, the specific conditions contributing to retreating blade stall should be evaluated and addressed accordingly. For instance, if high weight and density altitude led to retreating blade stall during a steep turn, rolling out of the turn may be the appropriate recovery. If low rotor RPM is the issue, increasing RPM becomes essential. Common errors in dealing with retreating blade stall include failing to recognize contributing factors leading to the stall and neglecting to calculate VNE limits for the altitudes to be flown. Helicopters equipped with articulating rotors, usually featuring 3 or more main rotor blades, are susceptible to ground resonance, a destructive vibration phenomenon occurring at specific rotor speeds when the helicopter is on the ground. This mechanical issue arises from the helicopter's airframe having a natural frequency intensified by an out-of-balance rotor. The unbalanced rotor disc vibrates at the same frequency as the airframe, and harmonic oscillation increases until it potentially causes the helicopter to self-destruct within seconds. Ground resonance may initiate from hard contact on one corner, especially with wheel-type landing gear. This contact sends a shockwave to the main rotor head, disrupting the normal blade relationship. If the RPM is low, the corrective action involves immediate throttle closure and fully lowering the collective to place the blades in low pitch. If within the normal operating RPM range, lifting off the ground and allowing the blades to rephase automatically is advised before making a normal touchdown. Dynamic rollover is a lateral rolling tendency that helicopters experience during takeoffs or landings. It occurs when the helicopter starts to pivot laterally around a skid or landing gear wheel. Factors contributing to dynamic rollover include a rolling moment, a pivot point other than the helicopter's normal center of gravity or CG, and thrust greater than weight. Dynamic rollover cannot be stopped by applying opposite cyclic control alone, and quickly reducing collective pitch is the most effective way to prevent it from developing. Critical conditions for dynamic rollover include right side skid or landing wheel down, right lateral center of gravity, crosswinds from the left, and left yaw inputs for counterclockwise rotor rotation. For helicopters with clockwise rotor rotation, the opposite conditions would be critical. It's crucial to consider these conditions to reduce the possibility of dynamic rollover and improve the chances of recovery. In helicopter maneuvers with one skid on the ground, adjust the cyclic control carefully. Consider forces like tail rotor thrust and main rotor dynamics. For instance, during a slow takeoff, failure to position and adjust the cyclic to accommodate translating tendency can lead to surpassing the critical recovery angle in less than 2 seconds. Maintaining proper cyclic position and preventing excessive roll and pitch rates are essential for control. Smoothly lifting the helicopter into the air while keeping pitch, roll, and yaw movements small is imperative, avoiding abrupt cyclic pressures. In normal takeoffs and landings on level ground, dynamic rollover remains a risk if one wheel or skid is on the ground with thrust approximately equal to the helicopter's weight. Proper execution of maneuvers is essential to prevent a roll rate from developing. Adjusting the cyclic to avoid building up pitch or roll movement rates is crucial, especially the roll rate. If the bank angle increases to approximately 5 to 8 degrees, and corrective cyclic input proves insufficient, reducing the collective is recommended to counter the unstable rolling condition. Excessive bank angles can result from issues such as landing gear caught in a tie-down strap or lateral loading imbalance. In slope operations, avoid excessive cyclic and collective pitch control into the slope to prevent upslope rolling motion. This visual illustrates the risk of the downslope skid or wheel rising due to these controls. Following published procedures during slope takeoffs and landings, and maintaining small roll rates, is essential. Raising the downslope skid or wheel gradually during takeoff and using combined cyclic and collective movements during landing can help maintain control. The collective is more effective than lateral cyclic in controlling rolling motion, as it reduces main rotor thrust. A smooth, moderate collective reduction is recommended to halt rolling motion, avoiding excessive rates. Abruptly pulling collective to get airborne may lead to an uncontrollable rolling moment. Excessive application of collective during slope operations can result in the helicopter rolling over on its side. Careful and precise control inputs are essential to navigate these maneuvers safely. To steer clear of dynamic rollover risks, it's essential to keep a few precautions in mind. First off, make it a habit to practice hovering auto-rotations, especially when the wind is acting up or exceeds 10 knots. Always be cautious around potential snags like fences, sprinklers, bushes, and other obstacles that could catch a skid or wheel. Pay attention to aircraft parked on hot asphalt overnight, as temperature changes might affect the landing gear. When lifting off, consider employing a two-step technique. Gently pull in enough collective pitch control to lighten the skids or landing wheels, ensuring equilibrium, and then smoothly lift the helicopter into the air. Maintain a comfortable height during hovering maneuvers close to the ground, particularly when practicing sideways or rearward flight. Take note of wind direction. If it's coming from the upslope, be aware that you'll have less lateral cyclic control. Avoid tailwind conditions during slope operations. Keep in mind that lateral cyclic control may change with varying passenger or cargo loads. If your helicopter has interconnecting fuel lines allowing automatic fuel transfer, be cautious of the gravitational impact on the center of gravity, affecting cyclic control application. Avoid pushing cyclic control to its limits. If you find yourself at the limit, bringing down the collective further might lead to mast bumping. Return to a hover and pick a landing spot with a gentler slope. When taking off from a slope, make sure to level the main rotor disc with the horizon or slightly into the slope for vertical lift. Only use enough lateral thrust to prevent sliding. If the upslope skid or wheel lifts before the downslope, smoothly lower the collective to check for obstructions. And when dealing with floating platforms, be mindful of dynamic rollover during flight operations, especially if the platform is pitching or rolling. Exercise caution around cranes, masts, nearby boats and nets. Plan your landings and takeoffs during periods of minimum wave motion for a smoother experience.